Okay, so we are going to up our game today with naming and drawing polyatomic ions. So what we're going to really look at today are the, oh dear, what's happening? The transition metals. So transition metals are going to need something special with them. And we are going to show their charge with Roman numerals. So don't forget, Roman numerals work like this. We've got 1 is 1, and 2 is 2, and 3 is 3, and 4 is IV, and 5 is V, and 6 is VI. That's about as high as we're going to go with these. So every time you see a transition metal, you are going to show its charge with a Roman numeral. So a Roman numeral of 1 means it has a charge of positive 1, and a Roman numeral 2 means it's got a charge of plus 2, and 3 means 3, obviously 4, 5, and 6. Now, the reason this is important is that some transition metals, like iron, they have multiple charges. They can be either, an iron atom can either have a positive 2 charge or a charge of plus 4. So in our naming, we would write that as iron 2 or iron 4, right? There's lots of transition metals like this, so we want to remember that. The other thing we're going to look at are polyatomic ions. So polyatomic ions are ions that are made of poly means many, and then you see atom in here, right? So many atoms in one ion. So we're going to have one ion that is like one ion, like it all fits in this blue circle, but it might be hydroxide. So there might be hydroxide, spelled like this, a hydroxide ion is OH negative. And what that means is that there's an oxygen atom and a hydrogen atom, and they're bonded together, and the entire thing has a negative charge to it. Or here's like another example, like permanganate. Permanganate is Permanganate. And permanganate is MnO4 with a negative charge as well. So that means in every permanganate ion, so all of it fits together in this blue cloud, you would have one atom of manganese with 4 atoms of oxygen, and they all work together as one big ion, and the whole thing has a grand total of a negative charge. So these are polyatomic ions, and they create ionic compounds also. So let's look at what this is going to look like. Like, let's say we have this. Let's say we have, for example, I'm going to tell you iron 3 hydroxide. Okay, here's the name. And I want you to tell me the formula, or draw it, as we would say. So that means I want to know the symbols. So you're going to say, okay, iron is Fe. This is telling me about its charge. So it's got a charge of 3+. Hydroxide, I recognize from my polyatomic ion sheet, and it is OH, and it has a negative charge. So this means that how many hydroxides do I need? And it's a lot easier sometimes if you envision it with brackets around it. So how many hydroxides do I need to balance my 3 irons? Well, I'm going to use my crisscross method. Crisscross. So that means I'm going to need 1 iron, so Fe, and I'm going to need 3 OHs. But I'm going to put a bracket around my OH in my final answer with the 3 as a subscript to show that there's 3 full OHs. Because here's the deal. If I wrote it like this, then that would mean that the 3 is only on the H. But I want the 3 to be for the entire OH, so therefore I have to use brackets. for that. Okay, let's try another one. What if we have, what if I want you to draw for me calcium cyanide? Calcium cyanide. So you're going to look at this and you're going to say, all right, calcium is Ca, and cyanide, I don't recognize that on the periodic table. It is on the polyatomic ion sheet, and it's Cn. So calcium has a charge of 2+, and cyanide has a charge of what? What is cyanide's charge? I can't remember. I think it's -2. So these are going to cancel each other out, right? So if I crisscross, that's a 2-to-2 ratio, which is the same as a 1-to-1 ratio. So I'm going to have Ca, Cn. I don't need brackets because I don't have multiple cyanide ions, if that makes sense. Okay, let's go the other direction. What if I give you this? FeClO3. All right, so what are we going to do here? Oops, I think I wrote that wrong. Reverse. 3 is on the outside. Okay, so I'm giving you this, and I want you to name it. So Fe is iron. And then I can see here that I have more than one atom, which means I need to look on my polyatomic ion sheet. So I'm going to go find ClO, and I believe you will find that this is chlorate. Okay, and chlorate has, all right, so here's the deal. There's 3 of them, and that's like a little red flag to me. So this iron is a transition metal. And if you have a transition metal, then what do you need? You need a Roman numeral. So I need to figure out what iron's charge was. So let's back up here. So there's 1 iron, right? And there's 3 chlorates. Well, if I was working in reverse order, these numbers would tell me about their charges, right? So I'm going to uncrisscross, which means chlorate had a charge of -1, and iron must have had a charge of +3. So I'm going to name this iron 3 chlorate, and that is my final answer. Okay, let's do one more. All right, let's say Be3 PO4 2. All right, so what is Be? Be is beryllium. Is beryllium a transition metal? No. Do I need a Roman numeral? No. PO4, again, multiple elements, so that must be polyatomic. I'm going to go look for PO4, and I think you're going to find that it is phosphate. So just plain old beryllium phosphate. Done, easy, out the door. The 3 and the 2 in this case did not mean anything to me. All right, that's really all you need to do. So just as a quick recap, transition metals get Roman numerals. Polyatomic ions get brackets if there's more than one of them, okay? And also as a reminder, you never show charges in your answer, okay? Those charges just help you figure things out, but they're not part of the answer. Okay, you guys are a bunch of geniuses. I'm sure you'll get this. Okay, bye, done, good job.